Hey everyone and welcome. Today we're diving deep into a super common but super important challenge in computer science. How do you ask questions about data in a tree and get an answer like right now? You know, whether you're trying to crush it in competitive programming or you're building massive systems, getting this right is an absolute game changer. So let's get into it.
So, let's start with a puzzle. Picture a tree with millions, maybe even billions of nodes. And I ask you to find the thousandth well, you get the idea, the 1,000th ancestor of some random node, and you have to do it in a blink of an eye. The obvious simple approach? It's just not going to cut it. This is exactly the kind of problem we're going to solve today.
So here's the plan. First, we'll talk about why the straightforward approach is a no-go. Then, we'll introduce a really clever technique called binary lifting. After that, we'll look at a totally different idea, flattening a whole tree into a simple array. We'll use these new powers to solve the famous lowest common ancestor problem, and then we'll wrap it all up with the key things you've got to remember for your next exam or interview.
All right, part one. First things first, what's an ancestor? Super simple, right? It's just any node you can get to by going up towards the root. Your parent, your parent's parent, and so on. So the obvious way to find, say, the 10th ancestor is to just hop up 10 times. But as you're about to see, in computer science, obvious is very often the enemy of fast.
And here's why. That one step at a time method takes O of k steps. That means if you want the millionth ancestor, you're doing a million operations. In a contest with a 1-second time limit, you're toast. This linear time complexity is our bottleneck. We need something way smarter. We need to get this down to logarithmic time.
And that brings us to our first awesome technique, binary lifting. This is a beautiful pre-computation method that lets us take these massive power of 2 jumps up the tree. It's basically the difference between taking the stairs one by one and having your own private express elevator.
This analogy is perfect. I mean, think about it. If you need to go up 13 floors, are you going to stop at every single one? No way! You hit the express button for 8 floors up. Now you're on floor 8. Then you hit the 4th floor button. Now you're on 12. And finally, the 1 floor button. You're there! 3 jumps instead of 13. That's the whole idea behind binary lifting.
So how do we build this elevator? We do a little bit of work up front. Before we answer any questions, we build this table. For every single node in the tree, we figure out where do I end up if I jump 1 step, 2 steps, 4 steps, 8 steps, and so on. We pre-calculate and store all of these power of 2 jumps. This O(n) log n setup time is what makes everything that comes next so incredibly fast.
And using it is a piece of cake. You want to find the kth ancestor? Just look at the binary representation of k. Every time you see a 1 in the binary number, you take that corresponding jump from your pre-computed table. So for 13, that's 1101 in binary. That means we make an 8 jump, a 4 jump, and a 1 jump. A few simple lookups, and boom, you're there.
So here's the deal, and it's a fantastic one. We pay a one-time cost of O(n) log n to build the table. It's an investment. But after that, every single query is answered in a ridiculously fast O log k time. If you have to answer thousands of these queries, this trade-off is an absolute no-brainer. It's a massive win.
Okay, let's switch gears completely. Our next big idea is a totally different way of thinking. Instead of jumping around in the tree, what if we could just, well, flatten the thing? What if we could turn this complex, branching structure into a simple, straight, one-dimensional array?
And it turns out we can, using a good old depth-first search, or DFS. You know how DFS works. It goes as deep as it can down one path before it backtracks. So if we just write down the nodes in the exact order we visit them for the first time, we get this special array.
The result is something like this. You can almost trace the path of the DFS just by reading the array. We go from 1 to 2 to 6. Then we backtrack, go to 3, and so on. Now, I know what you're thinking. This just looks like a random jumble of numbers. But trust me, there is a beautiful, hidden structure here. And here it is. This is the big aha moment. This is why we do this. Every single subtree from our original tree, no matter how big or small, is now represented by a perfectly continuous, unbroken block of elements in our new array. This is huge. Just look at this example. The subtree that starts at node 4 in the tree, it contains nodes 4, 7, 8, and 9. Now look at our flattened array. Would you look at that? 4, 7, 8, 9, all sitting right next to each other in a neat little block.
This means any question about a subtree can now be answered using powerful tools designed for arrays. It's a total game changer.
Okay, so we've learned how to jump and we've learned how to flatten. Now it's time to put it all together and take on one of the most famous problems in all of computer science, something you will absolutely see in an exam or interview, finding the lowest common ancestor, or LCA.
So what is the LCA? It's pretty intuitive. For any two nodes in a tree, their LCA is the shared ancestor that's deepest in the tree, the one that's as far away from the root as possible. Think of it as the first point where their paths back to the top of the tree merge.
So method 1 uses our new binary lifting skills. First, you get the two nodes on the same level. You take the deeper one and just jump it up until it's at the same depth as the other. Then you lift them both up at the same time, using those big power of two jumps until they're just about to meet. Their parents will be the same node, and that parent, that's your LCA. It's a really slick O of log n solution.
But what if I told you we could do even better? There's another, more advanced method that transforms this tree problem into a completely different kind of problem, something called a range minimum query, or RMQ. This is where things get really cool. To do this, we're going to do another DFS traversal, but this time we're going to record a node every single time we pass it, on the way down into a subtree and on the way back up. This is called an Euler tour, and for each entry, we'll store both the node and its depth. Now here's the magic. The LCA of any two nodes, A and B, is simply the node with the minimum depth in our Euler tour array between the first time we saw A and the first time we saw B. It just works. Why? Because any path from A to B has to go up through their LCA. So by turning this into a range minimum query problem and using some other data structures, we can actually answer LCA queries in constant O1 time. It's literally the fastest possible. And once you can find the LCA in a snap, you unlock all these other superpowers for free. For instance, finding the distance between any two nodes becomes trivial. You just need their depths, the depth of their LCA, plug it into this simple formula, and you're done. It's incredibly powerful. All right, that was a lot, I know. Let's take a breath and boil it all down into a practical toolkit, the stuff you really need to remember when you're staring down a problem in an exam. Here's your cheat sheet, your new toolkit. Number 1, binary lifting. When you see kth ancestor, your brain should immediately think of this. Number 2, DFS flattening. If a problem mentions queries on a subtree, this should be your first instinct. And number 3, for the absolute fastest LCA, remember the Euler tour trick that turns it into an RMQ problem. You know, we started with a problem that seemed really hard, finding a super distant ancestor in a giant tree without taking forever. But now you see, with the right way of thinking, it's not just solvable, it's actually pretty elegant. You've got the tools now, so the real question is, what else can you solve? Thanks for diving in with me.